Good morning, everyone. Today we're looking at Unit 2, Lesson 7, Polynomial Key Features, Part 2. So today we're going to look at a different key feature that odd and even polynomial functions have, and it relates to the symmetry. So the words even and odd, when applied to a function, refer to the symmetry that the graph of the function has. And I know we've talked about even and odd degree functions before, but we use the words even and odd also to refer to the symmetry, and I'll show you what I mean. So if we have an odd function, that is any function that has rotational or point symmetry. So rotational or point symmetry about the origin. So graphically, what I mean by that is if I was to take this half of this cubic function we have here, we have some type of cubic function because we have two turning points, right? If I was to take this half and I was to rotate it 180 degrees this way, 180 degrees, so keep rotating it, it would end up over here exactly on top of the other half of that function, right? So one half would end up on the other half. Maybe I'll do that in a different color, right? And the same is true as if I took this green end and I rotated it 180 degrees this way, it would end up exactly on top of this red end that we made here. So it would rotate and sit on top of the other half of the function, basically. How we show that out algebraically is that we say all odd functions have the property f of negative x equals negative f of x. So what I mean by that is when substituting negative x into the original function, all the terms in that original function, so all the terms in the resulting function are the opposite sign from the original function. Okay, so when we substitute a negative x into the original function, what happens is all the terms in the resulting function are the opposite sign of the original function. And we'll take it some examples so you can see what I mean here. So that is one type of symmetry that we could see with polynomials. This odd function means that it has rotational symmetry, or it rotates about the origin. So let's just draw here. Rotates about origin. All right, another type of symmetry that a function could have would be for us to say that it's an even function. So any function that has line symmetry about the y-axis. So what I mean by that in this case is if you look at what we have now, we have a quartic function. And if we drew a line of symmetry right on our y-axis, so let's say we had a line of symmetry, right? Think of this as a mirror, essentially. Okay. We have one half of our graph over here, and the y-axis creates this line symmetry. So we're basically going to reflect one side over the y-axis. So reflects over y-axis. So if we were going to do the reflection of the right side of my graph over my y-axis, the result would be the other half of our graph here, right? It would reflect over to the other half and lay directly on that half. So that's what it means to have line symmetry about the y-axis. So if we were going to explain what that means in words, we would say that f of negative x is equal to f of x. So basically when you substitute in a negative x value, you still end up with your original function. So let's say when substituting negative x into the original function, the resulting function is the same as the original. All right, so a function is neither even or odd if it doesn't meet the requirements to be an even or an odd function. So we would say it's neither if it doesn't meet the requirements to be an even or an odd function. One last point to make here, not to be confused, so don't confuse this idea of symmetry, so not to be confused with an even or odd degree. Right, when we're speaking about the degree of a function, we're talking about the highest exponent on the x variable. When we're saying that a function is an even function or an odd function, we're talking about the symmetry that is represented within that function. So without graphing, let's determine if the following polynomial functions have line symmetry about the x-axis, which again means that they are even, or if they have point symmetry about the origin, which means they are odd, or finally they could have neither. So let's look at this first one. So whenever we're trying to test for symmetry, we're always going to sub in f of negative x. Okay, and then we're going to see what is the result from doing that. So let's sub in f of negative x is equal to, and then everything I'm sub in, I'm just going to put in brackets so I make sure that I account for all the negatives where I need to. So f of negative x to the power of 4 minus negative x squared plus 2. All right, and we have to think about what happens with these negatives when we raise them to a certain exponent. Well, if I raise negative x to the power of 4, the result is going to be a positive x to the power of 4, right? Because if I have 4 negatives being multiplied, the result is going to be positive. If I have a negative x squared, well, again, the result is going to be just x squared plus 2. So if you look at what the result was with f of negative x and f of x, hopefully you see that these are the same. So we can say f of x, or sorry, f of negative x is equal to f of x. And if we look back up in our notes, that is true of an even function. So therefore, we have an even function because it has line symmetry. So if we were going to put this on a graph, we would see that we'd be able to reflect the graph over the y-axis. And it would look the same on the other side. It would be the mirror image. Okay, let's try another one. So if we have g of x equals x cubed plus 3x, again, we're going to sub in g of negative x. And you're going to get a negative x to the power of 3 plus 3 times a negative x. So we're going to try to simplify as much as we can. Well, if we have a negative x to the power of 3, we're going to end up with a negative x cubed. And 3 times a negative x is a negative 3x. Okay, so if we look at our original function, we can see each term is the negative version of the original one. So we would say g of negative x, is equal to the negative version of our original function, like that. So if you look up in your notes, when g of negative x is equal to negative gx, we're going to have an odd function. Because it has point symmetry, right? We could rotate it around the origin, and it would have the same graph on the other side of that. Okay, let's look at one more. So h of x, let's substitute in a negative x. Try that again. Negative x cubed plus 2 times negative x squared minus 3. So we'll start to simplify where we can. So negative x to the power 3 is going to be a negative x to the power 3. A negative x squared is just going to be a positive x squared. So we can just write that as 2x squared minus 3. So you see, if we compare this to our original function, if we were trying to identify if each term is now negative, well, that's not true. My 3 has the same sign on it. My 2x has the same sign on it. But my x cubed has a negative on it. So they're not all negative, and it's certainly not the same as our original function. So we would say, therefore, neither even or odd. And that's it for your note for today.